Okay, in this video we are going to learn what is an orthogonal and a unitary transformation. These are special types of transformations that have special properties for the transformation of vectors that they do, but also this translates into very special properties of the matrices themselves. And as you will see, these properties will be important in the next chapters of eigenvectors. Yeah? And they will also be very important in your further education in physics, like second year and ahead, and further than that. So let's have a look into this. I know there's a lot of new concepts here, but matrices is a huge topic. We would spend an entire year studying matrices, yeah? And here we're going to study all of the chapter 2 matrices in 3 weeks. So we have to go quite fast. So let's jump straight into it. So what is an orthogonal and a unitary transformation? Let's start with unitary matrices and unitary transformations. Okay, so what is a unitary transformation? This is the definition. A transformation A is unitary if and only if it does not change length of vectors and it does not change angles between vectors. So let me explain it. So this is a transformation that if you start with 2 vectors, let's say vector A and vector B, these 2 vectors have a certain length and a certain angle between them, yeah? And now we apply this transformation so the resulting vectors, they could be oriented differently, okay? They could be oriented maybe like this, A applied to A, and like this, A applied to B. But the length is the same after the transformation, and the angle is the same, okay? So an example of unitary transformations would be a rotation. Rotation doesn't change the length and doesn't change the angles between vectors. Another example could be a mirror reflection. So the angle between the vectors is the same and the length of the vectors is the same. Yeah? Now, when A is a transformation that is unitary, as usual, you can represent any transformation A as a matrix, as long as the transformation is linear. Yeah? So this means that there will be a matrix A associated with this unitary transformation. And this is called a unitary matrix, okay? And it has some very special properties. I am going to write the properties here, but I'm going to do a video which goes after this one with the proofs of these properties. These proofs, I would say, they are not obligatory for you to watch them, but I think they are quite beautiful. And if you are really interested in knowing why this is true, I would go watch that proof. It will be very fast. Yeah. But for now, I will just write the conclusions of those proofs. So, a matrix A is unitary if and only if A dagger times A equals I. So A dagger, the Hermitian conjugate of matrix A, multiplied by A is equal to the identity matrix. Looks mysterious, right? So you can have a look at the next video to see the proof of that. But we don't finish here. It even gets more interesting. And this is equivalent, so if and only if. So the 3 things I'm going to write are equivalent. The columns of A form an orthonormal set, which means that every single column of A has a unit length and is orthogonal to every other column of A. Okay? So this is quite fantastic, quite a great result. And as I said, in the next video, I will prove these two equivalences, okay? But for now, in this video, let's look at examples. So an example would be a rotation matrix, yeah? So remember, we found the rotation matrix in 2 dimensions, and we found it to be this one. So is this matrix unitary? Let's check. What would be A dagger? So A dagger would be the complex conjugate and the transpose, yeah? Since all these cosines and sines are real, then the complex conjugate doesn't do anything. So this would just be the transpose of the matrix. So it would be cosine theta, sine theta, minus sine theta, cosine theta. That would be A dagger, yes? Now we can check what is A dagger times A. So that would be this matrix times this other matrix. And if you do the multiplication of these two matrices, you get that the first element is cosine times cosine plus sine times sine. That's cosine squared plus sine squared, which is 1. The next element is cosine times minus sine plus sine times cosine. That's 0. This third element would also be 0. And the fourth element would be cosine squared plus sine squared again, which would be 1. And this is the identity matrix. Remember, the identity matrix is a matrix that has 1s in the main diagonal and it has 0s everywhere else. So yes, this is an example of a unitary matrix. So does this mean that the columns are orthonormal? So since this is equal to I, this means that A is unitary. And this must means that the columns of A are orthonormal. So let's check that. The first column of A is this vector, cosine theta, sine theta. And the second column of A is this other vector, minus sine theta, cosine theta. So basically, we are saying that A1 and A2 are orthonormal set. So their lengths must be equal to 1. So let's check that. So norm of A1 squared is the inner product of A1 with A1, which is equal to cosine squared theta plus sine squared theta, which is equal to 1. So yeah, it has unit length. Then A2 also has unit length. A2 inner product with A2, which is equal to minus sine times minus sine, that's plus sine squared theta, plus cosine times cosine, cosine squared theta, also equals to 1, trigonometric identity. And what about the angle between A1 and A2? Are they orthogonal? So A1 inner product A2, this is equal to the dot product between them, so that would be cosine theta times minus sine theta, plus sine theta times cosine theta, and this is equal to 0. So they are orthogonal to each other, and they have unit length. Therefore, they are an orthonormal set. So you can see how the rotation matrix is an example of a unitary matrix. So in the next, before we go to the next video, let's talk about what orthogonal matrices are, because this is very fast. So orthogonal matrices are the same as unitary matrices when the matrix is purely real. Okay, so when all of the matrix elements are real, then instead of calling it unitary matrix, we can call it orthogonal matrix. Okay, so A is orthogonal matrix if and only if And now instead of doing A dagger times A equals I, since I'm saying that the matrix is purely real, yeah, so we add the condition is purely real. So this means that A dagger is the same as A transpose. When the matrix is real, the complex conjugate doesn't change it. So A dagger is equal to A transpose. So A transpose multiplied by A must be equal to I. And then the columns are orthonormal. So when I was writing the notes, I wondered whether I should mention orthogonal matrices because they are it's the same as unitary matrices, but they are given a different name when they are purely real, and that's it. Okay, but the concept is the same as the unitary matrices. Excellent. So in the next video, I will prove this. So see you there.